Okay, in this last video on carbohydrates, we are going to look at disaccharides, polysaccharides, and at glucose metabolism. Okay? All right, so first let's look at two simple disaccharides, and these are going to form the basis of some larger polysaccharides that we're going to talk about in just a second. Okay? The two that we're going to talk about here are maltose on the left, over here. This is maltose, this one, and this is cellulose. If you look at them, there's really only one difference to them, in them, and that's the fact that this one is linked through, on the left side here, we have an alpha glucose, and on the left side here, we have a beta glucose. Other than that, these two are really the same compound. Okay, so they're diastereomers of each other. They're actually epimers. They're different at only one of the chiral center, this one right here. Okay? All right, so let's look at how these link up. All right, so we're going to just throw out a couple of new terms here. Okay, so this carbohydrate unit here in maltose, we're going to call the okay, sorry, I need to learn how to spell the glycoside donor. Okay? All right, so let's look at how it's linked up here. So this little part of the molecule right here is really the glycosidic linkage. And we refer to the glycosidic linkage in maltose as an alpha 1,4 glycosidic linkage. All right? So in the glycoside donor, what it really means is it's the member of the pair that donates the anomeric carbon, or where the anomeric carbon is part of the linkage. So here's the anomeric carbon here. Okay, here's the other anomeric carbon here. All right, so in this one, what we see here is that this anomeric carbon here is involved in the linkage. This anomeric carbon over here is not involved in the linkage. Okay, so we're the first term here is the alpha 1,4 glycosidic linkage. What it means is that in the glycosidic donor, which is the first one, its linkage is in the alpha position. Okay, if we number the carbons here, all right, you number from the anomeric carbon. Okay. What you see here is that carbon 1 of the glycosyl donor is connected to carbon 4 through the oxygen of the other molecule. The other molecule or the other monosaccharide is going to be referred to as the glycoside acceptor. It's really just the part of the glycoside linkage that is not the glycoside donor. Okay, so in polysaccharides and disaccharides, the glycoside acceptor is going to be a monosaccharide, but it doesn't. But the glycoside acceptor can be a variety of other things as well, or just a simple R group if that's all there is. Okay. All right, so we get maltose when we do a partial hydrolysis of starch. And well, starch is a polysaccharide, and we're going to find that the most common starch, amylose, is a very complex carbohydrate with a mixture of 1,4 and 1,6 alpha glycosidic linkages. Okay, cellulose here is the other one. We get this by the partial hydrolysis of cellulose. Okay, and what we see here is that if we look at the linkage, this is the glycoside donor. Okay, and we see here that it's now going in a beta orientation at the anomeric carbon, right? So we call this a beta 1,4 glycosidic linkage. It's also linked to carbon 4 of the acceptor molecule. Okay, all right, and again through the oxygen. Okay, hydrolysis of either of these will give you D-glucose presumably as a mixture of alpha and beta anomers. Okay, and we're going to look at these again when they become part of much larger polysaccharide systems. Okay, let's look at a couple of other common ones that we may have encountered sometime. Okay, this is on the one here is lactose, okay, which or milk sugar, and we call this one a beta 1,4 glycosidic linkage. Okay, and this carbohydrate over here is not glucose because notice here how it's different from the one that you see up there, right? So it's opposite. So this is actually galactose is the carbohydrate unit on the left, and the glycosidic acceptor here is glucose. All right. So lactose is kind of interesting. Most of us are familiar with milk sugar, right? So most of us probably, you can't grow up and not appreciate the fact that starch is nutritious or calorie containing and cellulose is not. It's just the woody part of plants. Okay, so what happens here is that humans have the ability to, or have the enzymes necessary to process the alpha glycosidic linkage, but not the beta glycosidic linkage. The only one that we readily process is the beta glycosidic linkage of lactose. You're born with that ability because you use milk, whether it comes from a cow or your mother or a goat or whatever, but it still has this linkage here. Okay, and if you don't continually consume lactose, you'll lose the ability to digest it because it has the beta linkage, so that's what makes it a little harder to digest. So you lose that ability if you stop continually ingesting it. Okay, and that's where the idea of lactose intolerance comes from. Okay, this is sucrose, or ordinary table sugar. Okay, and glucose or sucrose contains glucose as the it's hard to tell which is the donor and acceptor here because it's actually both of the linking carbons are anomeric carbons in this case. Okay, but sucrose on the left one in my structure here, and fructose over here. Sucrose is a alpha glycoside and very easily processed. Enzymes in saliva will break down sucrose into the component monosaccharides, glucose and fructose. Okay, we call this linkage here an alpha 1,2 glycosidic linkage. Again, it's not clear, 100% clear which is the donor in this case, since the both of the linking carbons are anomeric carbons. Okay, all right, so let's look at the property we most associate with sucrose, the fact that it tastes sweet. Okay, so sucrose, we're going to give this we're going to rate it here on something called the sweetness scale, and the sweetness scale is not a very scientific study. Each individual process is not. What they do is they take drinks at various concentrations of each of these and ask the person how sweet it is, and they say this is really sweet, this is not sweet at all, or whatever. And the idea here is that doesn't sound very scientific, but if you get a lot of people doing it, eventually you get rid of some of the error, and you can now develop the scale here. So sucrose is a 1. That's the standard by which all of the others are going to be rated against. Okay, glucose, hydrolysis product, is a little bit less sweet at 0.7, and fructose, the other part of this, is a little sweeter at 1.7. Okay, lactose, milk sugar, is not quite as sweet as sucrose at all. It's only 0.15. Okay, but some artificial compounds, actually humans taste them as being much sweeter than sucrose, the most common natural sweetener. Okay, so you can treat sucrose with thionyl chloride, and you don't let this reaction go to completion. The food industry has it all worked out, but you treat it with exactly the right amount of thionyl chloride, and you replace specific OH groups with chlorine, sometimes with inversion of configuration. Okay, so you replace this one and this primary one here, and this one, this equatorial OH becomes an axial OH there, and this is sucralose. Okay, so sucralose turns out to be much sweeter than sugar, 600 times sweeter. Okay, so you don't need nearly as much of it. Okay, a lot of people associated halogenated hydrocarbons with bad things like DDT and polychlorinated biphenyl and things like that. But this has been tested quite thoroughly. You don't really need very much of it. And here the chlorines are at sp3 carbon in this case. Okay, so this is sucralose, the artificial sweetener. All right, the oldest of the artificial sweeteners is saccharin, and this comes from back in the era of the 19th century when chemists would make a new compound. You'd see its boiling point, its melting point, its color, its refractive index, and another property you would see there is its taste. Chemists do not taste their compounds anymore for obvious reasons. We're worried about toxicity, but back in the 19th century, that was a routine part of chemical practice. Okay, I may have already discovered the world's perfect artificial sweetener in my laboratory because I'm too much of a chicken to taste it. I don't know. Okay, all right, so anyway, saccharin is this compound. As you can see, it has no carbohydrate-like structural characteristics at all. It just happens to taste very sweet. Okay, now my color scheme, what is it? Oh, it's the same color as the packets of sugar that you see on the table at the restaurant. Okay, so it's designed to conform to that. So sucrose is yellow, saccharin is pink, and aspartame is blue. Okay, all right, so saccharin is complete accidental discovery, and it's been around so long that you have to think that every test that could possibly be done with it has been done. I think in the 1970s or 1980s, someone gave rats the equivalent of 8,000 diet sodas per day, and a few of them developed bladder cancer, and it came off of the market for a while. But because all the other artificial sweeteners didn't taste nearly as good as saccharin, the demand by diabetics and people like who had problems with sugar really there was just a real major effort to bring saccharin back, and since then we now consider concentration as a factor in determining whether something is carcinogenic or not. In other words, back in there, it was considered that if it has the ability to produce a tumor at any concentration, it can't be used. But now I think we appreciate that there are certain low-level thresholds below which things are not carcinogenic. Okay, all right. Aspartame's kind of unique. It's not a carbohydrate. It's a type of compound we're going to take up in a couple of chapters. It's a protein. Okay, all right. So aspartame is this structure here, Aspartame, let's see, they call it, sometimes they call it nature's sweetener or whatever. I don't know that that's true. It's a methyl ester of a dipeptide. Okay. It doesn't have good heat stability because this nitrogen here, this lone pair, will attack the carbonyl group and give you a cyclic compound that doesn't taste very sweet anymore, so you can't use aspartame in cooking. Okay, so there's no real perfect artificial sweetener. You see a lot of claims like diet soda is poisonous, aspartame is deadly, but I've got to. It's hard for me to believe that you can, in a complex protein, that you don't have an aspartame and a phenylalanine unit beside each other quite frequently, and the hydrolysis or digestion of any protein is going to give, to some extent, some aspartame during the process. It won't be a methyl ester, it'll be a carboxylic acid, but I don't see where this is a completely artificial sweetener. I guess it would produce methanol as a byproduct, okay, of its metabolism, but for the most part, it's a protein. Okay, all right, so let's look at polysaccharides now. Okay, so starch or amylose is really just a mixture. It's basically like maltose, okay? It's a polymer of glucose with mostly 1,4-glycosidic linkages with a few 1,6 glycosidic linkages. Digestive enzymes readily process these alpha glycosidic linkages, like you see here. Okay, and turn the polysaccharide very readily into the monosaccharide glucose, which you probably appreciate is very digestible, eventually metabolizing to carbon dioxide and producing energy. Okay, so this is one of the major ways where humans produce energy from their food is by the metabolism of glucose. All right, merely isomeric with starch is cellulose, which we're going to refer to here as fiber. Okay, that's again a polymer of glucose, which has the beta-glycosidic linkages. One of the ways you can sort of tell these apart is when you draw them, cellulose stays at the same level, whereas starch, it has to be going down because of the alpha glycosidic linkages. All right, so humans can't digest cellulose, but bacterial enzymes in your large intestine can, and I think other creatures like termites and have this ability to process that. Cows have multiple stomachs that allow them to process cellulose as well. Okay, so this eventually will break down to glucose. If the organism can break down cellulose, it can use it as a fuel source, but we can't. Okay, glucose. These bacteria don't always just produce CO2. Sometimes some of them produce methane, some of them produce hydrogen, some of them produce carbon dioxide. This mixture here is commonly just referred to, for lack of a better term, as fart gas. Okay, so when you take in a lot of fiber, it goes completely through the small intestine and doesn't get absorbed, but you have bacteria in the large intestine that can process it. So when you have a high fiber meal, you don't get anything out of it, but for your bacteria, it's Thanksgiving for them, and they process it right away. That's why high fiber food produces farting. Okay, and we can also appreciate lactose intolerance. If you can't digest lactose, your body just sees it as another beta-glycosidic linkage, and the symptoms of lactose intolerance and I guess binging on fiber do produce very similar symptoms. Okay, we're going to, in this last one, just look at the glycolysis or breakdown of glucose in my actual class. This is not on the exam, but I just think we should look at it because they are really organic chemistry reactions occurring. This is really something you would be held more responsible for in a biochemistry class or a nutrition class or something like that. All right, so glucose is going to break down to pyruvate, 2 molecules of pyruvate here. Here we have 6 carbons. We're just going to cut it into 2 3-carbon pieces. Depending on the organism, a lot of things can happen at this point. Okay, pyruvate can go to lactates. Okay, through just a simple reduction of this carbonyl group. Yeast bacteria can turn pyruvate into ethanol. And another possible fate is that it's going to lose the CO2 to become a compound called acetyl SCOA. All right, and we're going to abbreviate that compound. And the key thing is that when it becomes acetyl CoA, the carbon-carbon bond is gone, and it's now a carbon-sulfur bond. Okay, the acetyl SCOA can transform to carbon dioxide as part of something called the Kreb Cycle, big thing in biochemistry. It can also serve as a building block for terpenes and steroids, and can also serve as a building block for fat molecules. Okay, so you've heard the term sugar turns into fat. Here's what it does. Glucose goes to pyruvate, which goes to acetyl SCOA and builds up into fat. Of course, if you're exercising, it'll all go this way to CO2 and energy, and a smaller amount of it goes into making steroids and related molecules. All right, so let's just look at it. There's 10 steps, but 5 are just phosphate movement. I don't mean to trivialize phosphate movement. It has a big effect on its water solubility, and its polar interactions with enzymes or other proteins and things like that. But we're just going to focus here on the things that are happening to the organic parts of the molecule. Okay, so I don't mean to trivialize phosphate movement. It can be important, and I think on your biochemistry test, it actually is going to be very important. Okay, but all right, so a variety of enzymes are involved in these processes. So adenosine triphosphate ATP is one of the major compounds that transfers or that converts alcohols into phosphate esters. Okay, so what happens here is that we're going to initially turn the OH at carbon 6 into the corresponding phosphate ester, and then we're going to use this enzyme phosphoroglucoisomerase to turn the glucose unit into a fructose unit. And this is a fructose. All right, so we saw how base could do that earlier in this chapter, right? And this isomerization proceeds through this type of intermediate here called the enediol. Basically, when we turn this enol back into a ketone, it can become a ketone, and it can be a carbonyl group at either carbon 1 or carbon 2. Okay, and the enzyme that moves this in a forward direction is phosphoroglucoisomerase. All right, we're going to put a phosphate at carbon 1 of our fructose molecule here. And now fructose biphosphate is going to do a process that's very familiar to us, one of our favorite reactions from organic chemistry, or the reverse of one of our favorite reactions, the aldol condensation. So this is the retro-aldol condensation and not the reto-aldol condensation as I've written there. And I'm going to show that in more detail on the next slide, but this basically cleaves the molecule between the carbon 3 and carbon 4 in a retro-aldol type reaction. Okay, so basically what's happening here is this is the type of reaction we're going to do. Let's look at this process in more detail. By the way, this gives you 2 3-carbon pieces, this dihydroxyacetone phosphate, and this one here, glyceraldehyde phosphate. Let's look at this in more detail. All right, so there it is, just that reaction right there. And again, as you can tell, I've been copying and pasting. The Rito is staying with us. Okay, all right. So here is glucose phosphate base. It's really an enzyme that's helping this out. It's not base all by itself. I'm just using base here, but we're going to remove this proton right here. This is going to give us this anion. Okay, this anion, the arrows I have in magenta signify a retroaldol condensation, and they produce the 2 pieces that we saw before, the glyceraldehyde piece and this piece right here, the enolate, which is going to get protonated to become the dihydroxyacetone piece. Okay, now we've cut glucose in half. All right, so each of these is we're going to take the glyceraldehyde piece and we're going to basically oxidize the aldehyde unit to the equivalent of a carboxylic acid, okay? And in these redox reactions in biology, we don't use chromium-6 and sodium borohydride. We use NADH, shown here, which says a hydride donor, or NAD+, which is a hydride acceptor. Okay, so the oxidation here, NAD+, okay, cofactor along with glyceraldehyde 3-phosphate dehydrogenase turns glyceraldehyde into this, I guess, glycolic acid. I don't know the name of that compound, but it's not the final step here. Okay, so we're going to turn this into this, and now this is going to oxidize again to pyruvate. Pyruvate can reduce with NADH to give you the lactate. Okay, yeast have the ability to turn this into CO2 and acetaldehyde, which further reduces to ethanol, and that's how ethanol is produced from sugar. Okay. And under aerobic conditions, this does an oxidative decarboxylation, okay, to give us acetyl SCOA. Okay, and CO2, and this is our precursor compound to fatty acids and steroids, which we're going to look at in the next chapter. Okay, all right, so I think that's it for carbohydrates. Again, you'll see this glucose metabolism in more detail in a biochemistry class, but I just wanted to point out the organic things that are occurring in that process.